Welcome back to the channel. If you are looking up to level your engineering game, you are in the right place. Today, we're tackling one of the big ones, scaling the monolith. We're breaking down the architecture of partitioning, how to handle massive data when your database starts to groan under the pressure. Before we dive in, do me a huge favor. Smash that like button, subscribe, and hit the bell icon so you don't miss our deep dives. Also, make sure to check out our companion site at www.bitbytoken.com. Whether you're software, data, AI, or machine learning engineering, our site is our home for foundational concept and high-level system design guides. Let's get to work. Slide number two. We all start a journey with a single table. It's elegant, it's simple, and it works perfectly until it doesn't. Imagine hitting that 1 petabyte breaking point. With 1000 user, life is good. But at 200 million rows, our database hits a wall. You've got index bloating eating up your RAM just to keep things running. Massive blocks like profile picture turning every simple read into an IO nightmare. And that looming dread of a single point of failure. One server, one bad day, and the whole house of cards comes down. Time to start cutting. First up, vertical partitioning, or the column cut. Think of this as the decluttering of your office. We separate data based on access frequency. Why drag a 5 MB profile picture into memory when they only need a 4-byte user ID? By moving heavy, rarely accessed columns like bio and profile pic into an extended table, we keep the core table lean. A 350 byte row can fit in your CPU cache. A 5 MB row absolutely cannot. We keep the row count identical, but we use the user ID as a structural bridge to link our two worlds together. But wait, there is no free lunch in engineering. That is the join tax. By splitting your data, you have introduced a new dependency, query coordination. Whenever you need to show a full user profile, you're forced to perform a join. If those two slices live on a different physical machines, that query is just transformed into an expensive cross-node network call. You've solved your IO problem, but you have opened the door for the latency overhead. What happens when the problem isn't the width of the table, but the volume of rows? That's where horizontal partitioning or the row cut comes in. When your index can go from microsecond to millisecond, it's time to divide the crowd. We keep the schema identical, but we slice the table into smaller, more manageable segments. The golden rule here, the architecture lives or dies by your choice of the partition key. Let's look at range partitioning. It's intuitive chunking data by continuous values like time. It's a godsend for reporting. The engine can use partition pruning to completely ignore 75% of your data, but it creates a write hotspot. If your users are active right now, 99% of the traffic slamming the 2024 partition, while your 2021 data sits idle, you've optimized for read, but you've created a massive bottleneck for writes. Enter hash partitioning. This is your algorithmic router. By hashing your partition key, you distribute writes evenly across all your nodes, effectively nuking that 2024 hotspot. Your point lookups for a specific user ID become instant. However, the trade-off is losing spatial awareness. If you need to run a range query for last week's order, the engine loses its ability to prune. It's forced into a scatter-gather operation, scanning every single partition. You can't have it all. Then we have list partitioning, explicit mapping. This is for when you need an absolute control, like for data locality or legal compliance. By mapping specific values to specific servers, like putting all EU users on EU servers, you ensure that sensitive data never physically touches US hardware. It's strict, it's precise, and it keeps your lawyers happy and your users safe. So, what's the difference between partitioning and sharding? It sounds like a debate, but it's really just a matter of scale. Partitioning is usually managed internally by a single database engine on one machine. Sharding is horizontal partitioning taken to its logical distributed extreme. Here, you partition across machine boundaries, and suddenly you need an external routing mechanism to keep track of where your data actually lives. Under the hood, sharding is a whole different beast. Local partitioning is transparent, but sharding is not. Your application layer needs to be cluster aware. You'll need middleware like Vitess or custom driver logic to route queries to correct physical node. That coordination layer is now your new critical point of failure and a major source of potential latency. The reality, at serious scale, you don't just pick one. You build a hybrid layered structure. You optimize metadata for latency and heavy content for throughput. You might use a vertical split to pull blobs out of the hot path, then combine that with horizontal hashing to ensure no single node gets crushed under the weight of traffic. It's multi-dimensional scaling. How does this look in the code? In modern Postgres, it's often declarative magic, just a simple partition by range command that the DB handles the boundary. But when you hit the sharding level, you're looking at application layer routing. Writing code that says, hey, find the shard for this user ID. It moves the responsibility from the database to your application logic. Here's your mental model for the interview, the two axis plane. You've got your y-axis, which is a row volume. That's where you're ideal with tall tables and sheer volume. Then you've got your x-axis, which is column width. That's where you deal with wide tables and mixed access frequencies. Every architectural decision is just choosing which axis to cut along to isolate the pane. When you are in the interview room, don't just recite definitions. That's the junior path. The senior path is about navigation. Start with your problem, define your trade-offs, present your solution, and then critically acknowledge the cause. If you suggest a hybrid split, mention the join overhead. Show them you understand that every architectural win comes with a price tag. And, and that's the architecture sign off. You now have the toolkit to start cutting up the monolith. But there is a question to leave you with. If you are using simple hat partitioning, what happens when you need to add a fifth server without rewriting your entire hash table and moving all that data? Think about that and let me know your solution in the comments below. If you found this breakdown useful, hit that like button, share it with your team, and subscribe for our next deep dive with consistent hashing. See you in the next one.